All right, yesterday we talked about and you practiced how to add vectors. So now we're going to look at the application of scalars and vectors. And your learning goal, I want you to be able to apply vectors to real world problems. Okay? So I have two word problems that we're going to go through together. And then I can explain some of the other applications that exist out there. So what is the biggest challenge today? Well, I've taken away your grid. You don't have a grid anymore. So panic sets in, but you're going to realize that the grid isn't really that important if we know lengths. So Tommy hiked 25 kilometers north, then 15 west, and then 8 north. We want to determine Tommy's final displacement. So key note here, displacement. Okay, this is a vector, which means we need magnitude or size, and we need direction in our final answer. Okay, so displacement's a vector. So you need to give yourself a quick sketch. So it doesn't matter where you start Tommy. Here's Tommy. He went north 25 kilometers. Then he went west. So as a reminder, for those that don't remember, never eat soggy worms. So there is your Cartesian plane, north, east, south, and west. So we went 15 kilometers west. So tail, head. I'm going to put the magnitudes in. And then 8 north up to here. 8. So there's his ending location. So there's the start. There is our end. So we want to know the final displacement. So displacement is a fancy word for resultant. We want to find the resultant for these vectors. So resultant starts at the starting point, ends at the ending point. So here is our, oh, my poorly drawn resultant. Let me try that again. That's better. So there's my resultant. So now you're saying, well, how do I get a right angle triangle out of this? Well, you kind of ignore everything except for the red vector. Your right angle triangle is going to go straight down and straight across. That's all there is to it. So there's my height. There's my right angle triangle. So now I just need to know the height of the triangle and the width. So back to grade 9, you kind of did this when you did volume and surface areas. I know that it's 25 kilometers up to this point and another 8. So 25 plus 8 is 33 kilometers. So I know the height of the triangle is 33. I knew he went sideways 15. So I have all my information. That's it. Once I've sketched it out for myself, I go straight to Pythagorean theorem. So a squared plus b squared equals c squared. 33 squared plus 15 squared is my resultant squared. Using my calculator, so 33 squared is 1089 plus 15 squared, which should be our 225, equals r squared. Adding those together, we get 1314. Square root both sides. And again, you can use the calculator to calculate it as a decimal. It's too much work for me to pull it up, so I just leave it as that right there. So there is my magnitude. That's how long the red vector is. Now I need to know a direction. And remember, the direction is always the starting point with your right angle triangle is the angle, which would make this opposite. It makes that adjacent every time. So tan theta equals opposite over adjacent. Tan theta equals 33 over 15. That I cannot do in my head. So remember, with the calculator, you need to do the fraction first. 33 divided by 15 equals inverse tan 65.6. So therefore, Tommy is the square root of 1314 kilometers. Now his direction Here's the starting point. Okay? We went this way, which is west. So we went west. Then we turn 65.6 degrees toward the north, and we start heading north. So we went west, and then we went north. And that's it. That will give you Tommy's location after he has traveled in those three directions. All right, so we're just adding those vectors together. And the difference, again, from yesterday compared to today is that you just don't have a grid. Second and final example then, Tommy hiked at 4 kilometers an hour. So now we're talking about a velocity. So it's a speed with a direction. And then we also have a time in here. And then 2 kilometers east, and finally 5 kilometers an hour north. Find Tommy's final displacement. I didn't type that in. We need times for these ones. So put for 1 hour. And let's say for 2 hours. All right, so make that addition to the question. So basically what's happening here, if you think back to yesterday, if I called this first vector u, and I called this vector v, and this vector w, basically what's happening is that because he's traveling for 3 hours, he is doing 3 u vectors, then he is doing 2 v vectors, oops, not 2 v vectors, my mistake, plus a v vector, because we just said it's for an hour, plus he's doing 2 w vectors. All right? So all this question is doing is making you add the vectors up the right amount of times. So that first one, okay? So Tommy hiked 4 kilometers an hour north for 3 hours. So he did it 3 times. So he went north. So 4 times 3 is 12 kilometers. So in that first leg, he went 12 kilometers. Then went east for 1 hour. So in 1 hour, he would have went 2 kilometers. In the final one, he went north again. And he did it for 2 hours. So 2w, 2 times the 5 gives me 10 kilometers. So that's really the only difference between this example and the previous example, is dealing with these multiples. So it just affects your diagram, because if you look, here's a starting point, here's the end point, I draw that vector in, and voila, there's my resultant. The tricky part for a lot of people is drawing that right angle triangle. So what I always tell them is your starting point, just draw a big line across, end point, draw a line down, where they intersect is where your right angle triangle exists. Okay? Some of you will see that right away, but for some people that struggle spatially, like myself, you have to kind of have some tricks in there to help you find that triangle. The angle we're interested in is always down here inside the right angle triangle at the starting point. Now we're all set. Figure out our distances. Well, we know we went 12 and 10, so we went a total of 22 kilometers north and just 2 kilometers east. So I have my lengths of my right angle triangle. A squared plus b squared equals c squared. So 2 squared plus 22 squared is my resultant squared. 4 plus, not in my zone, I can't do the 22 squared today in my head. Probably not in the average day. 484 equals my resultant squared. So 488 equals r squared. Take the square root of both sides. And the resultant then is the square root. And again, you can use the calculator. If square root signs freak you out, get rid of it. Use a decimal. So the resultant is 488, square root of 488 kilometers. The angle's always tan theta, so that's kind of nice. I don't have to think too hard on what trig ratio. The only thing I got to be careful of, if this is my reference angle, I have opposite and adjacent. So 22 over 2 tan theta. So again, always do the fraction first. So 22 divided by 2 is 11. Just proving my calculator works. And I get an angle of 84.8. So 84.8 degrees. So therefore, Tommy is located the square root of 488 kilometers, and the angle or the location based on the triangle I drew. I went east first and then north. So I went east, leave a space, north, and the angle you found out always goes in the middle. And there you go. So there is your two application questions. Now, where would you use this probably more commonly in real life, or where have you gentlemen or ladies seen this? AutoCAD, okay, or SketchUp. So, real examples. All right, AutoCAD, SketchUp. All right, if you go into geography, okay, if you're looking for a field as a geographer, it'll come up. Now, AutoCAD and SketchUp, if this is, see if I can draw my house. Okay, so there's my house. AutoCAD or SketchUp always has that reference point, right? That's where the house starts. What it does is it says, oh, this wall, here's the vector, okay? So this wall is, say, 15 feet east. This wall is 20 feet, and it's going into the page. And what it does is it stores every wall you put in there, it stores it as a vector. So the walls are stored as vectors. So what it can do, it can take vectors and it can find area of a wall using vectors. It can find volume of the house using vectors. So it's all tied together, and that's how a lot of these base programs work, is with your vectors. Okay? With your geography, you use it in terms of your orienteering. Okay? Also locating locating reference points in terms of elevations and so on and so forth. So vectors, there is a lot of applications out there. If you get into another construction example would be total station. Total station is something that takes survey information, but it converts it all to vector information. So there is lots of applications out here. Remember, we're at the base steps here. This is setting you up to be successful if you continue into a college program working with these vectors. So anyway, any questions with homework, I will gladly give you a hand. Let me know what's needed, and we'll see you next time.